Hello everyone, this is Lecture 1 of ComSci 174, Introduction to Computer Vision. In this video, we will introduce computer vision and talk about its main ingredient, which is the images. We will also talk about the tasks and applications for computer vision and the challenges that come with it. So let's start with cameras. We know that cameras are everywhere nowadays, right? So we have digital cameras, we have action cameras like GoPro, we have surveillance cameras for CCTVs, we have cameras in drones nowadays, we also have cameras on computers and on our phones, right? On our smartphones for taking selfies and other pictures, right? So cameras are everywhere, okay? You can see them everywhere, and with the abundance of cameras, of course, the result of this would be there will also be an abundance of images and videos. Okay, so just from Instagram, for example, you have about 95 million videos and photos that are being uploaded daily. Okay, and then on Facebook, you have 300 million photos that are being uploaded daily, and on YouTube, there's 300 hours of video per minute that's being uploaded. So that's a lot of image and video that is being uploaded daily and even per minute, right? So can you just imagine how much space this consumes on their database or on their data warehouse, right? So yeah, that's the reality nowadays. There's a lot of images and videos in our daily life. So where does computer vision fit in this? So since we have a lot of images, what can we do with these images to make it useful? So computer vision is basically giving computers the ability to see. Okay? So Dr. Fei-Fei Li of Stanford said that if we want machines to think, we need to teach them to see. Okay? So in the quest for artificial intelligence, wherein the machines could think and have intelligence, in order to achieve that, we have to teach them or enable them to see or have a vision of the world. Okay, so that's where computer vision comes in. So formally, computer vision is a branch of artificial intelligence. Okay, and its focus is on analyzing images and videos to give computers visual perception. Now, when we talk about perception, it's not only limited to seeing the scene or the environment. So perception comes in three parts. You see, you describe, and you understand. Okay? Because if you just want to see, then the camera is enough for that. But computer vision does not only limit its scope to just basically seeing the environment. Okay, so it also has to understand and describe what is happening. So that is perception. Okay, not just seeing but also understanding what you are seeing. Okay, so that is the hard part of computer vision. Is basically how do you make the computer understand what it is seeing, because seeing is easy, right? You have the camera for that. Okay, so computer vision combines image processing, pattern recognition, and image understanding. So it's a combination of the three, because image processing is of course used to make the image more easier to process for later steps, and then for pattern recognition, that's used to get features and some patterns for pattern matching. And then of course image understanding is when you tie it all up together and actually understand or perceive what you are seeing. Okay, so that's computer vision. So computer vision is related to other branches of science like biology and psychology. So it's related to neuroscience and cognitive sciences, because we need to be able to figure out how the humans see and understand what it is seeing, right? So some knowledge of neuroscience and cognitive science would be handy, right? And then of course for computer science and math, you have the machine learning part, the algorithms, the graphics and systems and theory. that would also come in handy as well. And then from physics, you have the image processing, and then for robotics, for engineering, it's also related because, of course, some robots would need vision for them to be able to function fully, right? So it's related to a bunch of other fields as well. Now, um, for humans, the purpose of vision is basically two main things, right? First, we use vision as a measurement device. Okay, so we use our eyes to perceive how far away something is. Okay, how big an object is, or yeah, the size of the object basically. So when you have, for example, the Mars rover, um, it needs vision for it to be able to see the obstacles along the way. Okay, so is that a big rock or a small rock? Is the rock far away or already near? Okay, so that's the purpose, measurement device. And then you can also do this to reconstruct the models of a building, for example, and we do that by um, knowing the depth and the relative size of the object based on images. Okay, so you can do that. Vision as a measurement device. But the main purpose of vision is as a source of semantic information, basically understanding what you are seeing. So from this picture, we could label the parts of the picture, like, for example, this is the Ferris wheel, this is a tree, there's water behind it, there's a carousel here, there's a tree, another tree here, and so on. Okay, so semantic information, meaning we can label the parts of the images based on our understanding of the environment. Okay, so those are the two main purposes of vision as a um, for measuring as a measuring device and for semantic information. Okay, so for the human vision, we use it to estimate distance. Okay, how far is an object, um, or yeah, basically, especially if you're traveling, right? So how far is the other car or the uh, the the car behind you? So you can estimate that based on your vision. And then of course recognition. Okay, quick recognition of face, objects, and actions. So when we see someone, we can immediately recognize that, hey, this is my friend, this is my enemy, or something like that. Okay, or if you don't recognize it, then hey, this is a stranger. Okay, and then of course objects. When we see things, we automatically recognize that, oh, this is a pen, or this is a computer, or this is a phone or something, right? So it's almost instantaneous. Okay, and then of course action. So when we see people or other things that move, do something, then we can recognize their actions. Like, for example, is the person standing or walking or motioning for you to come to him, like, hey, come here, or maybe he's waving goodbye or something. So we can also quickly recognize actions, right? And then of course we use our human vision to see patterns. So we are very good pattern recognition machines, our human vision system. So um, especially, for example, if we have things like finding like where's Waldo in the game, where's Waldo. So even if the image is very convoluted and very busy and very yeah, confusing, just by finding the pattern of Waldo's, usually we use the shirt, the striped red and white shirt to find Waldo quickly, right? So just by finding that pattern, then we can quickly see it. And then because of this pattern recognition, we sometimes also do this to clouds. So I don't know if you have done this, but like, for example, you see a cloud that looks like maybe a rabbit, or a cloud that looks like a heart. So it doesn't really I mean, the cloud did not really form like this pattern by its like by itself, but because of our prior knowledge of shapes and how rabbits look like, or maybe a dog that's sleeping, something like that, we can see a pattern even if it's not intended to be like a pattern, right? So I hope you get what I'm saying. And the human vision is even it can even work even with bad settings, right? So even if it's blurry, or if it's dark, or you have bad lighting, the human vision can still somehow function. Okay, so even if, for example, it's foggy, or if you're wearing glasses, you can't see, but you can still make out some of the, like, maybe you can't recognize the face, but you can recognize that there is a person standing there, right? Or even in dark or bad lighting, we can still somehow see like silhouettes or shadows, which tells us that there is something there, right? So yeah, even in bad settings, human vision still works. However, the human vision is not perfect because it could be fooled by optical illusion. So, for example, this one. This is not a video or a GIF. This is a just an JPEG, right? So, but if you stare at it long enough, like if you focus on some of the dots, it would appear as if it's moving, but it's actually not. So, just example of an optical illusion. Okay, so the brain or our visual system is fooled into thinking that this is moving when in fact it is not. Okay, so yeah, it's because it's an optical illusion. Okay, so the way that the human vision works is shown here in this step-by-step process. So we have this scene here, and we acquire an image of the scene using our eyes, right? So that's the image acquisition part, and the image is being sent to our brain for interpretation. Okay, so the image interpretation part is done by the brain, and that is when we perceive that, okay, I am looking at some kind of road where there are trees on either side of the road. So probably I'm in the rural area, maybe, because there's a small likelihood that this is in an urban area because of the abundance of trees, right? So yeah, you can perceive what the environment is based on this scene. So that is for human vision. Now for computer vision, it's more or less the same, but we replace the eye with the camera and the brain with the computer. So from this to this. Okay, but basically it's the same. So the image acquisition is done by the camera, and then the image captured by the camera is sent to the computer for processing and for analyzing, and that's when you do the interpretation part. Okay, and that is when you get the perception. Okay, so it's more or less the same, the process. It's just that we have different tools that do the acquisition and interpretation. Okay, so that's computer vision. Okay, now as humans, when we see a picture, for example, it's very easy for us to label the parts of the picture, right? So given this picture of a tiger, we can see that this is the back of the tiger, this is the tail, there's the shadow of the tiger there, these are the legs, the mouth, and so on. Okay, and we can even see that, like, this region here that's highlighted, that is the part that has the tiger. Okay, and we can label other things like this part is water, this part is grass, this part here is sand, and so on. So it's easy for us because of like stored knowledge ever since we were children, right? But for computers, it's very different. Okay, because what the computer sees is basically just a bunch of pixels. Okay, so given this image, the computer sees pixels. So basically an image is just an array of pixels, right? So it's a 2D array of pixels or brightness values. So it doesn't really know yet, unless we train it to recognize that this is a tiger. It doesn't know that this is a tiger. It just knows that these are the pixels in this image. Okay, so the computer sees an image which is just a big grid of numbers between 0 to 255. Okay, so for example, in the image of this cat, we could zoom in on this part here, and this would be the what the computer sees. So it's just a bunch of numbers. So it's really a big leap from numbers to knowing that this image is a picture of a cat. Okay, so there's a big gap from numbers to perception, and that is the gap is supposed to be bridged by computer vision. Okay, so let's discuss images, because images are what the computer vision uses for all of its tasks, right? So images, you've encountered images from your, probably even since ever since you were a child, you've seen images already, right? So a computer image is a 2D array of pixels. So it's a two-dimensional array of pixels. Pixels are basically just brightness values. Okay, it's a number from 0 to 255. And when you're colored, when the image is colored, you usually have 3 channels for the image. You have the red channel, the green channel, and the blue channel. So you have the RGB value, right? So pixels, as I've mentioned, are brightness values that range from 0 to 255. So 0 is the dark, so meaning if it's 0, meaning there's no brightness at all, so it's black. And then if it's 255, that's the maximum brightness. So if you have 255 on all 3 channels, you have the pure white. If you only have 255 on red and then 0 on green and blue, then that would be pure red. And then the same for 255 on green and then 0 for the rest, that would be pure green. And then 255 on blue and 0 on red green, that would be pure blue. So we will learn more about this in our next video, which would talk about color spaces and this thing. So but for now, yeah, pixels have the range from 0 to 255. And other images are also can also be in grayscale, so meaning it only has one channel, and it's not colored, so it's black and white. Not just black and white, but black, white, and gray. And then depending on the value of the grayness, it could be light gray to dark gray, so depending on the value from 0 to 255. Okay, and then there are also other color spaces like the HSV, which we will discuss in later videos. But yeah, those are images. Okay, so there's a lot of source of images. Okay, so from our personal images or personal photos, like family photos, and then images from the movies, right? So videos are basically just a bunch of images that are sequenced together, right? So even if it's a video, that's still made up of like millions of images, okay, or thousands or hundreds, depending on the length of the video, of course. And then you have images from news and sports broadcasts, and then you have images from surveillance, right, like in CCTVs. And then you have medical images like mga x-rays and CT scans, and even what are this, maybe some science thing, so scientific images like microscopes. And then you also have satellite images, and then space images, right? So there's a lot of sources of images and types of images that we could encounter. And then of course there are also the images that are being uploaded by users to like Google and other image uploading sites. And then of course you have YouTube or Instagram and so on. So there's a lot of images, is basically what I'm saying. Now, with all of these images in hand, what can we do with them? So what are the tasks for computer vision? Okay, so usually we divide the tasks into 3 levels. Okay, so there's the low level tasks, which is concerned with image processing. And then the next are mid-level tasks, which are concerned with grouping pixels together. Okay, and then the high level tasks, which are about recognition. Okay, so those are the 3 levels. So let's start with low level vision. So for low level tasks, this concerns with image processing, basically. Okay, doing something with a pixel, so processing the pixel to achieve some effect. Okay, so we'll learn more about image processing in next videos. But basically for low-level vision, you are working with individual pixels or local neighborhoods. Okay, so it's pretty basic and it's pretty fast. You can do it quickly because you're just working on the pixels itself. So some of the tasks that you could do in low-level vision are image matching. Okay, so you can match images, like for example, I know that this is a picture of the Eiffel Tower and this is also another picture of the Eiffel Tower, although they are two different pictures, right? This one is the baseline is somewhere here, and then this one has this bridge at the bottom. So these are two different pictures, but we know that they are both pictures of the Eiffel Tower, basically because we can match the features here, like this one matches this one and so on. So those are just pixels and point features, corner features. Then you can also do things like image stitching. Okay, so from a bunch of images, you can stitch them together to form a big image. You can do that. And maybe the one that you've seen is the panorama feature on your phone. So if you take like a long, if you long press it and then you gradually move the phone from left to right, then you capture a lot of different images, and then this will be stitched together to form the panorama image. Okay, so that is also an application of low-level vision. And then you also have optical flow, which basically detects the part of the image that is moving in a video. So yeah, if you see it here, the points that are colored indicate that there is motion from the previous image to the next image. Okay, so that's optical flow. Okay, so that's low-level vision, basically just per point basis or per pixel basis. Now for mid-level vision or middle-level vision, we now move up one step, and instead of just working on individual pixels, we will group them together. Okay, so we're now grouping pixels. We're looking at surface attributes like contours and textures and other features, right? So we can group the pixels together, and we can now infer geometry, shapes, and 3D models, and then we can also infer motion. Okay, so what are some of the tasks for mid-level vision? So first you have segmentation. So segmentation is basically just separating the parts that you are interested in from the background. So foreground, background segmentation is like one of the basic tasks in computer vision. So in this picture, for example, you want to separate the two firemen from the background, or from here you have the plane from the background, and then here you have the penguin from the background. And then there are different levels of segmentation, like for example, the penguin is here, and then there's also the ground here that's being segmented. Or you could also just include the ground as part of the background itself, and then just have the black-white segmentation. Okay, and then here on top you have like detailed levels of segmentation, like this part is segmented differently. So this is the hat, and then this is the head, and then this is the body, and then this one is different again. So this is the hat, the head, and the body. So different levels of segmentation depending on what you want and what you need in your application. But basically it's separating parts of an image from other parts. Okay, some more examples of segmentation. So you have the monk here, so you have the robe, which is being segmented differently, and then the background is also segmented differently, right? And then you have the parasols here, the yellow parasols, or I don't know if this is just a big umbrella. Yeah, so the yellow parts are here segmented, and so on. So that's segmentation, and we can use this for self-driving cars. So for self-driving cars, they have to see what's in front of them, right? So for them to be able to process what if there's an obstacle, if the road in front is free from obstacles, then you have to segment it first, right? You have to separate or you have to group together pixels to be able to maybe form like a car. So this is a car, so there's an incoming car, so I have to avoid it, something like that. Or if there's nothing, if it's just purely the road that you can see, then you can just fully go ahead, right? So that's helpful for self-driving cars. And then for medical imaging, segmentation is also being used to separate the or basically to separate different parts of the images. So if there's a tumor that is present in the image, you can quickly detect it. Okay, so segmentation is also important in medical imaging. And then next, you also have 3D reconstruction. So as we said earlier, we could infer geometry or shapes. So from a bunch of images, okay, 2D images that are taken at different angles, if you get enough images to cover the whole 3D object, then it is possible for you to reconstruct the 3D object or with a model, okay, just based on a bunch of 2D images. Okay, so I'll show another example later in the later part. And then next is stereo vision. Stereo vision is basically seeing with two eyes or two cameras, basically. So stereo is two eyes or two cameras. So with stereo vision, it enables you to perceive depth. Okay, because if you only have one source of the image, if you have one camera, then you have this let's say this first image. Now if you only have one image, you're not sure if a object which appears to be small is actually small or if it's a big object that's far. Okay, so we don't know that, it's ambiguous. But if you have um, two cameras and that capture the same scene at the same time, then you can infer the depth. So for example, based on these two images here, we can compute the depth, which is the depth map here. So the deeper you are or the farther you are, the bluer it will get. So red is near, so like this, and then blue is far, so something like that. So it allows you to detect distance. So that is why if you have like only one eye, or if you like, for example, you're a pirate. Imagine you're a pirate with an eye patch. Sometimes if you only use one eye, it's hard for you to estimate the distance. So you might bump into tables a lot or chairs because you thought that the object was still far away, but in fact it's not. And that is because you are not using stereo vision, but you're only using single vision, which is one eye. Okay, so two eyes is important to be able to perceive depth. Okay, other mid-level tasks include object tracking, so tracking the motion of the object. And then you can use this for surveillance. Okay, so you can track different people even if they are already moving. Okay, so yeah, that's mid-level vision. And then for the last part or the last level, which is high-level vision, so this is now about understanding, this is about recognition, this is about semantics. Okay, so you can put labels on things. Okay, so of course it's important to put labels on things, right? You don't want things to be ambiguous. Anyway, okay, so what are the high level tasks? So you have the first is object detection. So you can detect that there's a car here, or there's a traffic light somewhere here, or there's a bus. Okay, so detecting objects, putting a bounding box on that object in the image. So yeah, another example here, you have cars, a dog, a horse, and then a person and another person. So you detect objects basically. So this is important, and you can apply this in motion capture. So for example, in Pirates of the Caribbean, the actors were only looked like this on the set. Then they have these things that are markers, like the dots here, and those are detected by the software, so that it's easier for them to put the computer graphics. So for example, the the hat can be placed here, or this part of the I don't know what to call them, the pirate or the monster is placed here, and so on. So it's easy to detect these circles and then add um, the graphics easily because of the landmarks. Okay, and then of course you have human detection, detecting humans. So also for surveillance, and then face detection, of course, right? So you've seen a lot of this, like in Snapchat filters, Instagram filters. How does it know where to put the the tongue and the nose and the dog ears, right? So it's because it has detected your face. And then of course you have the face swap, if you've seen this before. So it produces some creepy things, yeah, but you can swap two faces basically. It's because you've detected the two faces. But of course it's not perfect because you can swap like the oranges and the banana with your face, which is kind of weird, right? And even the cat's face can be um, swapped with with the child here, and then the Barbie's face was or I don't know if this is Barbie, but a doll basically, a doll's face with the child. So some of these are creepy, but yeah, you can do that. And then what's even more creepier is something called the face to face. I'm not sure if you've seen this, but basically the idea is, so you have the target actor. In this case, this is George Bush, and then you have the source actor. And then what you can do is you can combine the expressions of the source actor and make it look like the target actor is doing what the source actor is doing. So you can do really uh, um, really creepy stuff with this. Like you can make someone you can make a video that makes it look like Duterte is like, or the President Duterte is like declaring martial law or something, or whatever, right? Or like someone is saying gossip about you, and you catch that on video, but in reality it's really just a manufactured video, right? So I don't know if this is a really good thing. Not sure if, yeah, but this is one application. So anyway, yeah. Hopefully it won't be used for evil things. Now, on to more positive things. You have smile detection, right? So some cameras have this. When they detect a smile, they automatically capture the picture, right? So I remember I had a camera before that did this. Okay, and then next is object recognition. So you recognize or classify the things that are being detected. So for example, here you have orange, banana, a cat, a monitor, and so on. So this would be useful in things like Amazon Go. So Amazon Go, if you haven't heard of it, is basically a store wherein you could go in and then take the things that you want, and then there's no checkout, there's no lines, because what they do is um, on before you go out, they have a camera that looks at the things that you took. Okay, so the items that you bought, and then using object recognition, they will recognize what those products are, and then just send the bill to your Amazon account. So yeah, object recognition is being used for that. And then of course you also do this for biometrics. Okay, so recognizing whether the fingerprint that was being input is actually yours. Okay, or even in iris recognition. And then you also have character recognition, optical character recognition, or OCR. So letters and numbers are being recognized basically. So you do this for license plate readers, automatic check processing, even a Sudoku grabber. Um, so yeah, character recognition. It's this is pretty basic, like um, letters and numbers. And then you have face recognition. So of course, um, you've probably encountered from before when Facebook did the automatic tagging of your face even without your permission. So that's because it was recognizing that this face actually belongs to you, right? So and then you have things like iris recognition. So the story behind this picture is that in 1985, like a photographer took a picture of this girl from Afghanistan, and then he didn't know who the girl was, and then later on they matched and found this Afghan girl by matching the patterns on her iris. So by her eyes, even if she looks older now, the iris patterns remain the same. So they were able to find this girl years later. Okay, and then of course you have recognition of action. So like recognizing what the person on the video is doing. So is he doing boxing or clapping or walking, jogging, and so on. Okay. Okay, and then next is image classification, which is one of the most common tasks for object recognition. So given an image, is that an image of an airplane or a bird or a cat and so on? So yeah, just classify the image based on the given labels. Okay, and then you also have scene understanding. So given a picture, you can label the parts. So understanding that this is the bedroom, this is the bed, another bed, and then there's a chair here. So you're basically labeling the parts of the image, right? And then another example here is this is a vehicle, the green is vehicle, the blue is these are buildings, and then the light blue is sky, black is background, and the red is are pedestrian. Okay, and then the orange is the ground. So it's basically labeling parts of the scene. Okay, so you're understanding what the parts are by showing the semantic labels. Then you also have content-based image retrieval. So it's basically searching using images. Okay, so if you want, if let's say you have an collection of images of flowers, and then you input this one, like give me the images that look like this. Okay, so if you do that, if we do search, usually we do search with words, right? But when we search with images, how do we actually compare and then say that this image is similar to, let's say, this one or this one or this one? Okay, so there's sort of a pattern matching and understanding that the features here are similar to the features here and so on. So that is content-based image retrieval. So you've probably seen this in the Google image search. So instead of inputting a keyword, you input an image and it will show you visually similar images. Okay, so how does it do that? So basically there's a comparison of images from the one that you gave and the ones that are already existing in the database. Okay, now with all these tasks, when we do computer vision, we usually follow the feed-forward approach. And what we mean by that is we start from the low level, the image processing, using the pixels and local neighborhoods, and then we move up to the mid-level, so we group them up together for segmentation, and then finally, that's when we do the high-level recognition, right? So by feed-forward, we mean that we start with low level, and then we pass it on to mid-level, and then we pass it on to high level. So it's a 3-step process that goes through each level separately. Okay, now another way that we could organize computer vision tasks is by using the 3 R's of computer vision, and that would be recognition, reconstruction, and reorganization. So recognition, of course, is basically recognizing what the thing is. Reorganization is about grouping pixels together, so segmentation. And then for the reconstruction, this is about 3D imaging, 3D modeling. Okay, so recognition is about recognizing objects, activities. Reorganization is segmentation, which is grouping pixels into objects. And then reconstruction is about forming the 3D structure. Okay, so those are also the 3 main tasks of computer vision. Okay, so now that we've seen what we could do with computer vision, how do we apply it in the real world? So these are the application fields of computer vision. So first is on human assistance. So you've probably seen Google Glass, right? So using this glass, it sees something. You can do search using the glass itself, and so that one uses computer vision. And then for games like Kinect, okay, so it has to recognize that you're doing a spike or something. So it has, or if you're dancing, then it has to recognize your actions, and using the sensor, it would process that and send it to the game itself, and make sure that your moves are mirroring what the avatar is doing, right? So that's also applicable in games. So that one is also computer vision, because you're allowing the game console to view, or to see what you're doing, and in return do the same thing that you are doing. Okay, and then of course you're in sports, you can also apply image processing, like for example overlaying this yellow line marker here in football. So you can also do that. And then in movies, of course, it's easier to do to apply the computer graphics, because of the computer vision techniques that we can do. Okay, so on the set it looks like this, and then after processing the image, looks like they're apes. And then 3D modeling. So for example, in this one, there's a lot of cameras here that will capture the face of former President Barack Obama of the US, um, at different angles. So this cameras here would capture that, and then it would reconstruct Obama's face in a 3D model to create this bust. Okay, so it's like an accurate um, representation. So it even has the moles and the little details here, right? So you can do that with computer vision. So based on 2D images, so a lot of 2D images, you can combine that to form the 3D model itself. Okay, so and then of course you have the augmented and virtual reality, AR and VR. So you have things like the Oculus Rift, right? So you can also do that, and that is an application of computer vision as well. And then of course for transportation, you have the self-driving cars now, and the way that the cars are able to drive by themselves is because they have cameras that look at the streets and look at the pedestrians and the traffic light, and they process everything. They process what they're seeing, and then feed that to the self-driving system, um, which tells them whether to stop or go forward, and whatever, right? So transportation is also another field where computer vision can be applied. And then of course you have surveillance, so tracking people on a CCTV. You can also do that. And then for security, of course, so you have things now like the Face ID in iPhone. Okay, so it recognizes that this is your face. Um, and how does it do that? So of course it has a model, or a picture of you, or yeah, of your face. And then even if you change your hairstyle, or like you've maybe put on makeup or something that changed your appearance up slightly, it will still recognize you. Okay, so it's kind of robust that way. And then you can also use it in health and medicine. So as I mentioned earlier, you have things like the medical images in MRI, CT scans. Okay, so you can use computer vision and image processing to simplify and clean up the images, to for us to be able to or not us, but for the doctors to be able to use the image more easily. Okay, and then you also have things like image guided surgery. Okay, so they can guide you where to, maybe, I don't know, open up the skull here, I think is what they're doing. Yeah. Okay, and next you have the things in science. For example, so you have a picture of a cell from probably from a microscope, and then you can do automated cell segmentation. So you can separate them into different parts. So You can also do that with image processing. And then agriculture, so maybe you have a camera that keeps track of your plants, and whether they are already ravaged by bugs or caterpillars and whatnot, right? And of course, you can also do this for fisheries. So I was part of a project before wherein what we did was we basically did surveys or like census of fish underwater. So what we did was we took a camera rig and made it stay for about 15 to 30 minutes underwater, and then the fish would just pass by through the camera, and then we would take the camera out, and then for processing we would detect the fishes and recognize their species, the fish species. So we could count that there are, let's say, 20 tilapias or 30, I don't know, bangus or whatever type of fish that was. So yeah, basically like a census of fish um, underwater. Yeah, so it's also applicable there. And then of course robotics like the Mars rover and autonomous remote controlled car. If they can see what the terrain is or the environment is, then they could probably make appropriate actions, whether to avoid or to slow down or to speed up and so on. And then you can also apply this in manufacturing, so automated manufacturing, like maybe there's a camera there that will keep track of like defects, like the label was put on backwards or the cap is not present and so on. So for automated manufacturing, this is already very common. Okay, so those are the fields or applications. Those are just some of the fields that you can apply computer vision. Of course there are many more, but those are just some of the few that are common. Now the final part that we'll talk about would be the challenges for computer vision. So what makes computer vision challenging? So let's go through each one. So first is viewpoint variation. So what does this mean? So basically viewpoint variation means that you can take a picture of an object at different angles, and for us humans it would seemingly look the same, but for the computer it would be totally different. So for example, if I take a picture of this cat at this angle and then I move slightly, just slightly to the right, like I tilt it to the right a bit, then the image that I would capture on the next one would be very different from the image that I captured on the first one. And why is that? It's because the pixels change when the camera moves. So it would be a totally different bunch of numbers now from the one earlier. But for us humans, we could identify that, hey, those two are similar. It probably the change is even probably negligible, right? We can't see the slight difference. But for the computer, which can only see numbers, it would be totally different now. Okay, so if we change the angle slightly, or maybe the lighting change, like when you put on lighting on the same object, and then even if it's the same angle but the lighting is different, then the image would also be different now, because the pixels would become brighter, presumably because you have better lighting. Okay, so once the environment changes, the pixel values will also change. So that is one challenge. And then, as I mentioned, illumination changes things. So we know that these are pictures of cats, right? But because of illumination differences, it might be difficult for the computer to recognize that these are cats. So like for example here, it's slightly dark around the background, and then with better lighting around the center. Then this one is just like the cat, you can't even see the cat's face on the second one, right, because of poor lighting, and on the fourth picture as well. So it's like just a silhouette of a cat here. Whereas the third one, this has the best lighting out of the four, and you can see the cat's face clearly. Okay, so with illumination differences, the pictures of the same object could look different, entirely different. And as I mentioned, the computer only sees pixel values. So if it sees a totally different pixel value, it might assume that, hey, this is a different object altogether, when in fact it's the same object all along. It's just that the lighting changed. Okay. Next, you also have deformation. So if, let's say, we just focused on teaching the computer to recognize cats, okay, so maybe cat detection or cat recognition is what you're doing. So as humans, we can see that these four pictures are pictures of cats, but then for the computer, this would be challenging because this cat is like lying down, this one is totally lying down, then this one is like on two legs, and then this one is like chilling and sitting down, right? So it has four different poses, and maybe we teach the computer that the cat is usually on all fours or maybe lying down or something, but then because of the variations in pose, so it's kind of deformed, right, or twisted, and has a different shape, so it might be difficult to generalize what a cat looks like for a computer. Okay. And then next is occlusion. So occlusion is basically being hidden, okay, or being occluded, or having like something in front of you, or not really clear that you are the foreground. Okay, so you might blend with the background. So for example, here we can see the cat hiding behind the blanket, and even behind the grass here, and then the third one, it's hiding under the couch pillows, I guess, but we can see the tail, so we know that there's a cat there. So if the object is hidden, of course the computer would find it very difficult to detect that there is a cat there, because it cannot clearly see that this one is a cat, this one is a cat, because of the other objects that surround it, and that possibly hinder its ability to see the actual object itself. But usually when we see things in the real world, it's not in perfect settings, right? Most things are occluded. We might just see like a part of a person's face, or a part of like the object that you're looking at, but we can still recognize that, hey, there's a cat under this blanket, or hey, that one is my friend, even if I can only see half of his face. But for computers, if there's occlusion, then it's usually a challenge for them, okay, because it basically differs from the what it learned, is the basic, or like the usual appearance of this object is, okay. And then adding to that, you also have background clutter. So sometimes when the object itself blends with the background, and then it's now even more difficult for the computer to figure out, or maybe even segment, because in the first picture, the cat is also orange, like orangey brown, like the ground itself. Okay, so it kind of looks like the cat is blending in with the background, so it would be difficult for the computer to segment this one out. And then the same with the second photo, the fur of the cat is white, like the snow on the background, so it might be difficult to trace or to segment where the part which part of this is still part of the cat, or which part is already part of the ground itself, okay, because of background clutter. And then there is also intra-class variation. When we say intra-class variation, this just means that in the same class, or in the same type of object that we're interested in, there is still variation, right? So this is an example. This, we know that these are 5 kittens, right? But they look different from each other, right? So this one is orange, this one is brown and white, also brown and white, and then this one is brown and I think oranges, I'm not sure. Then this one is also quite similar, but you can see that even if they are the same the same class, so we know that they're kittens, but they look different because of their colors. So intra-class variation, and it's not even limited to just colors, even the shape itself. So we know that this 6 are pictures of chairs, but this chair looks different from this chair and this chair and this chair. So even if it's the same class, so intra-class, within the class, there is variation, which makes it difficult for us to generalize what the chair is, right? So yeah, that's also another challenge. And then on top of that, there's also inter-class similarity. So in inter-class similarity, on the other hand, you are now looking at two different classes. So in this one, you have the cat and the dog, and then there are similarities between them that makes it hard to put a fine line on what is a cat and what is a dog. Like, for example, both of them are fluffy. They both have fur. They have 4 legs, and they're both lying down. They have 2 ears and a snout and whiskers and so on, right? So even if they are different from different classes, a dog and a cat, but they have a lot of similar features, or similar features. So that is also another challenge for computer vision, because then how would you know which one is which? Okay. And then of course there's also motion. So when the object is moving, sometimes it becomes blurry, right? So if we capture it perfectly, like you have the eagle that is pretty much visible, and then the background is blurry, or if you focus on the background is pretty visible, but then the eagle is blurry. So when you have motion, then you tend to have blurry images. So, and then again, when it's blurry, it makes things difficult for the computer. Then of course there's also inherent ambiguity. Like, for example, is this a picture of a duck or a rabbit? So I'm sure you've seen this picture before. So is this a duck or a rabbit? Depending on which part you look at, it could be both, it could be either one. But yeah, so those things, some pictures are inherently ambiguous. So how can a computer know which is which? So another example of ambiguity in pictures is this one. So is this a really big Coca-Cola bottle, or is this just an optical illusion? This one is just actually a street art drawing, and just based on the angle that the photo was taken, then it looks like the bottle is really big, right? So it's ambiguous for the computer if this is a really big bottle, or like a bottle that is very near and the person is really small. So it's not quite clear, right? And then there's also local ambiguity. Like, for example, if the picture is blurry, and then if you only focus on this part, so it looks like there's a black, like, rectangle like object here, and then this one is quite similar as well. It's black rectangle. This one is also like a black rectangle here, a black rectangle here. So if you're just given this part, like the black rectangle, is this part from here, from here, from here, from here, from here? You don't know, right? Because it's localized. So without the context of the bigger picture, you cannot tell which part this one is from. Okay, so especially if it's blurry and there's not too much information. So yeah, the computer will also struggle with that. Okay, so yeah, those are the challenges, and this is where we will stop for now. So in summary, for this video we talked about the computer vision. So we introduced computer vision. So it's basically giving the computer the ability to see, and it's only not just limited to seeing, but it's actually giving visual perception, so seeing, describing, and understanding. Okay, we talked about images, how they are a 2D array of pixels, and pixels are just brightness values that range from 0 to 255, and basically a computer sees just a bunch of numbers, right? And then we talked about the different tasks and applications for computer vision. So from the low-level tasks that focus on the individual pixels, and then mid-level tasks that focus on grouping those pixels together, and then finally on high-level tasks that focus on recognition. Okay, and then we also talked about the different fields that we could apply computer vision into, and then finally we tackled some of the challenges that you could face when doing computer vision. So that's it for now. For our next topic, we will introduce OpenCV, which would be our tool for doing computer vision. We will talk about image manipulation, image arithmetic, and color spaces. And just a reminder, please make sure that you have installed the Python version of OpenCV so that we could start with our exercises next time. Okay, so after we introduce OpenCV, then you will now have an idea of how to use it, so we can start with our exercises. Okay, so that's it for this video. If you have any questions, please let me know, and I will see you in the next video.